initial part of kinetics, there will be some calculations involved. The students need to be able to come up with a rate expression of a certain reaction, okay? The first thing that they need to understand is that the rate expression can only be deduced through experiments. There is no other way, okay? And then they need to know that the general formula is like that, is rate is equal to a rate constant multiplied to the concentration of the reactant to a certain order, concentration of another reactant to a certain order, and it can just continue on depending on how many reactants are involved in the rate determining step. Okay, so usually for this you need to also explain like what is K, what is like the order of reaction. Okay. So this part mainly involves finding out the order of reaction based on the data given. So usually I will give you a series of reactions, 1, 2, 3, and then, oh, is it too small? Then they will give you the concentration. Okay, so for example 0.1, 0.1, 0.1, 0.1, 0.1, 0.2, 0.1, and they'll give the rate, and then you're supposed to deduce the rate from here. Okay, there are 3 order. Mainly in IB chemistry, you only need to explain about 0 order, first order, and second order. Yeah. So they can do it mathematically, but usually IB only requires them to say something like the rate is 0 order with respect to A, for example, because when the concentration of A is doubled, the rate stays constant, something like that. Okay, and you can say it's first order with respect to A because when concentration of A is doubled, the rate doubles. Or second order with respect to A because when the concentration of A is doubled, the rate is quadrupled. Okay, so that's basically it. And students need to know the graph. 2 types of graph. One is rate against concentration, and another one is concentration against time. Okay, for all three orders. Okay, 0 order, first order, and second order. Okay, and then in the reaction mechanisms, the students are supposed to come up with a possible mechanism for the reaction. Okay, this is usually a chapter that the students are very confused with because it's very broad and there is not only one correct answers. They need to come up with it themselves, but usually we say that they must follow 3 rules. Okay, one is the total of all the steps must give you the overall equation. Overall equation, okay? And not more than 2 species per step. Okay? And then thirdly, the rate determining step has to give rate expression in accordance to the calculated or deduced from 16.1. So usually they will give you data, and then you will find the rate expression first, what order, and then the reaction steps that you propose, okay, must also give the same rate expression. Okay, for example, I have an equation like this, okay, 2a plus b giving me c. Okay, and then they give data, and from the data you deduce that the rate expression is like this: k, a, b. Okay, something like that. So what types of mechanism can you come out with? For example, I can say I put a plus a giving me x, which is an intermediate, and then x plus b giving me c, which is a product. Okay, why is this a possible rate mechanism? Because when I total these two steps, I will get 2a plus b giving me c, which is my overall equation. And the second point, each step I do not have more than 2 species. Okay, but now for the rate determining step, we can deduce, okay, maybe if I say this is the RDS, okay, or sometimes they will just have to write it this way: slow and fast. This is one possibility, or this is fast and this is slow. Okay, now we have to see whether it fulfills our third rule. Now, if this is a slow step, okay, then my rate expression should be k a, because my slow step depends on 2 species a and a, okay, or a to the power of 2. Which means if my reaction mechanisms are like this, and this is my slow step, my rate expression should look like this. Okay, but this one is different from what is given, okay? Which means this cannot be the slower step, okay? So now, if this is the slower step, okay, then my rate should be x and b, okay? But again, be careful, our x doesn't come out here, so we have to see whether x depends on anything else, and we know that x depends on the two a's. So we can change it to a, b. So I'll get k a square b, which again doesn't tally with this one, okay? Which means this reaction mechanism, although it fulfills the first two rules, it doesn't fulfill the third one. So this cannot be the correct mechanism, okay? Then you can come up with another one. You can say that, okay, then I'll react A with B first to give me X, and then X will react with the remaining A to give me C, okay? So this total will give me this one, so it's possible. Each step doesn't have more than 2 species, and actually if I say that this is my slow step, I will get this as a rate, okay? So this is a possible reaction mechanism. Yeah, so there are other, for example, I can say A will turn to X first, and then X will react with B to give me Y, and then Y will react with another A to give me C, okay? So if I say this is a slow step, okay, again this in total will give me the overall equation. Each step is no more than 2, and if this is my rate determining step, I'll definitely get this as a rate, okay, if you work it out. So it's another possible reaction mechanism. So because of the nature of the uncertainty of this type of question, students are usually a bit confused, like on like how to come up with this. But after a while, after enough practice, they should be able to get it pretty fast. Okay? So that's about reaction mechanism. And then the last one is activation energy. Activation energy revolves around this equation. K is Arrhenius equation. Okay, what the students need to know is that when you take ln on both sides of this equation, you will have this equation which is actually a straight line equation. Okay. Students who did math or additional math in O levels or IGCSE SE should know about this. Okay. So this is like a straight line equation where your y-axis is ln k, your x-axis is 1 over t. Okay, so when you plot a graph of ln k and 1 over t, okay, the gradient will be minus EA over r, okay, and the y-intercept will be ln A. Okay, so from here, okay, you can actually find the activation energy. Okay, gradient is minus EA over R, so activation energy is R multiplied minus R multiplied by the gradient. Okay, so this is one thing that students need to know. And then ln A is equal to y-intercept, so A is e to the power of y-intercept. Okay, so this is another way of finding the activation energy and A. A is a constant, we call it Arrhenius constant. Arrhenius constant deals with the collision geometry. Remember the collision theory where it involves, or where the molecules involved need to have energy over the activation energy. So you can find the activation energy here, and it must have correct collision geometry. So this is the factors that affect collision geometry, all summarized in Arrhenius equation, Arrhenius constant. Okay. Another thing that you need to take note while teaching this, that you need to teach students that the gradient of this graph must always be negative, because see, gradient is minus EA over R. If the gradient is not negative, R we know is the ideal gas constant from chapter 1. Okay, and ideal gas constant is always positive. Okay, so if this is not negative, your activation energy will be negative, which is impossible. Okay, so your line should always have a negative gradient. On top of that, your line can never cut the y-axis. Okay, in order to get the y-intercept, you need to extrapolate, because the x-axis is 1 over t. You can never get a 0 in a reciprocal, because your temperature, well, it's always positive anyway, but you can never get 0 for 1 over t. So you always stop here in the middle, and you have to extrapolate to get ln A. Okay, the extrapolation is very reasonable because this is a straight line graph.